Hi, my name is Sophia Levana and I'm a student at University of California, San Francisco, and today I'm going to talk to you about the Doppler effect. This is my second video on the Doppler effect. In my first video on the Doppler effect, I gave a basic background on sound, a definition of the Doppler effect, and several examples of the Doppler effect. In this video, I'm going to begin discussing how the Doppler effect works. And I'm going to start out by discussing how the Doppler effect works conceptually in this video, and then get into how the Doppler effect works physically in my third video. Before we can build a conceptual model of the Doppler effect, we need to go back to our definition of the Doppler effect. When we defined the Doppler effect in the last video, we decided that the Doppler effect was the change in the perceived frequency of a wave when the observer is moving relative to the source. And when I'm building a conceptual model of the Doppler effect in class, I start out with a bucket of ping pong balls. And I pick them up. Here's me and my bucket, one at a time, and I throw them at my students. And I use these ping pong balls to model a wave in which I am the source of the wave, and my students are the observers. And as the source of the wave, I throw my ping pong balls at a set frequency. And we know that frequency in physics is the number of events per unit time. And so, I can model a wave by throwing ping pong balls at a set frequency of one ball every 2 seconds. And we can think about the Doppler effect by considering how the frequency perceived by the observer, f prime, changes. So in this model, I am the source of the wave, throwing ping pong balls at a frequency of one ball for every 2 seconds, and my students are the observers, perceiving the wave at a frequency of f prime. So generally, when I begin to throw the ping pong balls at my students, they're sitting still. And so, the frequency at which they perceive the ping pong balls is the same at the frequency at which I throw them, and f prime, the perceived frequency, is equal to f. Most of the time, though, they don't stay still for very long, and as I begin to throw ping pong balls, my students begin to run away. And so, when the observer runs away from the source, my students get hit with ping pong balls less frequently. So the perceived frequency as the observer moves away decreases. Occasionally in class, there's 1 or 2 bold students who decide that instead of moving away from me as I bombard them with ping pong balls, they're going to move towards me. And students who move towards me as I throw ping pong balls at them get hit more frequently. So when the observers, or the students, move towards the source, the perceived frequency, f prime, increases. And this makes sense. When someone is throwing something at you, your instinct is to run away in order to get hit less often. And if you run towards the source, you're going to get hit more often, and the frequency at which you get hit will increase. So now that we've modeled what happens to the perceived frequency when the observer moves, let's add a little bit of complication and talk about what happens when the source moves. So if I am standing still at the front of the classroom and my students are sitting still, the perceived frequency, f prime, is equal to the frequency at the source, f. But if I pick up my ping pong balls and I begin to walk towards my students as I'm throwing, they're going to get hit more often. So when the source moves towards the observer, the perceived frequency f prime increases. In contrast, if I pick up my bucket of ping pong balls and I start to walk out of the room, still throwing one ball every 2 seconds, my students, who are sitting quietly in their desks, get hit less and less frequently as I walk away. So as the source moves away from the observer, the perceived frequency decreases. So now we've built a conceptual model of the Doppler effect using ping pong balls thrown at a frequency of one ball every 2 seconds as a model of a wave. Let's just wrap this up by moving back to our definition of the Doppler effect. I'm going to erase this writing over here. But I'll leave our table that discusses what happens to the perceived frequency as the source moves relative to the observer, or the observer moves relative to the source. So, let's wrap up right now by just discussing one final model, which is the model I used to define Doppler effect in my first lecture. And in this model, I had a dinner bell as my source, and a man with big ears as my observer. And when I ring the dinner bell, I generate a sound wave with a frequency f from my source. And there's a man with big ears who acts as an observer and perceives this sound wave with a frequency f prime. If my man begins to walk away from the dinner bell, the perceived frequency of the sound wave, f prime, decreases, the same way it did when the students ran away from the ping pong balls. If my man with the big ears walks towards the dinner bell, the perceived frequency, f prime, of the sound wave increases, the same way it did when my students, who were bold, began to walk towards me as I bombarded them with ping pong balls. So that wraps up my conceptual model of the Doppler effect. And we'll use this model to discuss how the Doppler effect works physically and what equations we can use to describe it.